Thank you so much for nice and great introduction. First of all, I would like to say thank you so much for inviting me here. And this is a great pleasure to have this talk here. And I hope that at the end of this presentation, I can bring you a fair understanding of the quantum teleportation, somehow quantum mechanics. So let me share my screen to start our lecture here. I think I guess I need access to be able to share my screen.
Okay, let me see. Okay, can you check now?
Yeah, it worked.
Okay.
Okay, let's start our presentation today. I'm going to talk about the quantum teleportation, different aspects of it, and we're going to understand how different it is. With what you see in the science fiction movies. And we have to go step by step in order to be able to fully grasp the mathematical and experimental beauty behind this concept. So at the first place, let's have a deal. Speaking generally, you can say there are two kinds of language in the quantum mechanics for description of events and phenomena. There's first one, Heisenberg picture, and the second one is the Schrödinger picture. We don't have to do anything just to deal the details of these languages here, but all we need to know is in Schrödinger picture, basically use the differential equation, but in Heisenberg picture, we use the metrics. And this is the language we're going to use in this presentation today. In the Heisenberg picture, there's one important point that we have to know for our presentation. This X here, and you see this creature here is just a cat. And it's a kind of Dirac notation. It was Paul Dirac who first time introduced this cat into the quantum mechanics. It's coming from linear algebra. And on the left side here, you see it's X. This is basically representing the wave function of a quantum system, can be a photon, electron, or something. A wave function, it's supposed to give you all the information you need about the quantum systems. And this wave function basically lives in a Hilbert space. It's a complex vector space. And you want to show that quantum state, you need some basis here, for example, x1, x2, and x3, which represent different possibilities of that quantum system. And you have coefficient A, B, and C here. These coefficients are related to probability. In other words, you can say, for example, you do a measurement on the quantum systems here. The chance to find this quantum state in this possibility of x1 is a squared. The chance to find it in the possibility of x2 is b squared. And the chance to find it in the possibility of x3 is c squared. And you want to know what's the meaning of this cadence wave function? It's just a unit vector in higher dimensional Hilbert space. So let's have this deal. And now we go ahead. Speaking of teleportation, the first picture probably you're familiar with it is from the Star Trek, one of the most famous movies here. And I guess you watch lots of science fiction movies about the teleportation, and this should be this way. There is a chamber. Some people enter this chamber. You see some light pulses, a strange voice, and after a while, you see that those people appear in another planet, galaxy, or somewhere else. This is the general picture we have once we think about the teleportation. But how about the quantum mechanics and how it works in the quantum mechanics? In the quantum mechanics, when we say quantum teleportation, it means this picture. consider you have two persons here. The first person on the left side is Alice. She lives on the earth just like me and you. The second person is Bob on the right-hand side, and he lives on the Mars, hopefully in the future. Alice already has a quantum state, which can be a photon here. This phi 1 is just a wave function of her quantum states, and this can be a photon in polarization, linear polarization states. For example, a superposition of horizontal and vertical. This spin up here is vertical, and this spin down here is horizontal polarization. Alice wants to send her photon to Bob, but not physically sending or transferring this photon. Alice wants Bob to have an exact copy of her quantum state or photon without physically transferring this, without physically taking this photon from one place to second place. This is the concept of teleportation. So the first question that you might ask yourself is why we don't do that, just like whatever we do in the classical, our classical world every day. For example, you want to make a copy of lecture notebook or somewhere else, you just get some information of that thing, that physical object in our microscopic worlds, and then you make a perfect copy. I'm going to tell you this cannot happen in the quantum mechanics because of two reasons. The first reason is because of the nature of measurement in the quantum mechanics. Imagine you have this photon state here, just like the first slide that I talk about the quantum state here. This photon state basically can be in a superposition of two situations, the 0 state and the 1 state. And you want to do a measurement on this photon. And this is the port that you do the quantum measurement. In the classical physics, once you measure quantity about any physical object, there is always certainty. You can say that this is the result of the measurement. So after that measurement, if you don't have any error, whatever you measure, whatever times you measure, you're going to get the same result. And this makes sense. This is the common sense in our world. But in the quantum mechanics, it's not. There is just randomness here. After the measurement, the chance you find this photon on the 0 state is just alpha squared. The chance to find it in the 1 state is just beta squared. No matter how many times, for example, 10,000th time you do the measurement of polarization on this photon, you just get the randomness here. This is the probability you get this one. This is the probability you get that one. As an example, look at this photon. It can be in a superposition of horizontal and vertical states here. And this one is the probability coefficient. You want to calculate the probability, you have to consider the square of this one. It means 50% or 1/2 chances to find this photon in horizontal polarization and 50% chances in the vertical polarization. Let's get back to a classical world we experience every day. Imagine electrical circuit. At the output of the electrical circuit, there might be a superposition of the voltage level. You want to measure the voltage? We can say, for example, it can be 0 volt, it can be 5 volts. In digital world, you can say this 0 corresponds to 0 level, and that 5 volt can be corresponding to 1 level. But that superposition is not the real one. And it's different with the quantum mechanical superposition. Before measurement, doing the measurement on the quantum mechanical aspect of this photon, there is no way that to say which one is the polarization. Basically, this photon doesn't have any specific feature before the measurement. So that is the first reason you cannot make a copy of quantum state, because if you start doing the measurements onto a physical object to get information about that, you're going to change the quantum state. It's not this previous quantum state anymore. This is the first reason. The second reason is no cloning theorem. Mathematically, you can prove, and this is a very famous proof in quantum mechanics, that there is no quantum operation. There is no way to make a perfect copy of any quantum states. So the photon that you make, you want to make a copy of that cannot be cloned. This is the second reason. So now the question is how we can make that possible using the teleportation, quantum teleportation. It seems like a black magic, but it is real. Imagine, again, you have this Alice here and Bob here. Alice wants to teleport her photon, initial photon to Bob. It means we want to have this photon at Bob's side at the end of the experiment, I'm going to show you this is possible and it's already happened, that using a source of entangled photons, which we called EPR, and it stands for Einstein, Podolsky, Rosen, because these guys were the first guys introduced these entangled photons by using two channels, the classical channel, the quantum communication channel. It is possible. And let's see how it's possible. But first, what is the magic here? The magic is the quantum entanglement. Maybe the most surprising feature of the quantum mechanics, which makes a huge difference between classical physics and quantum physics. In funny language, we can say it's kind of love in physics, because once you have two entangled photons, it doesn't matter how far they are, even how far in time aspects they are. You do a measurement on one of these photons, entangled photons, immediately, right after that, it affects simultaneously the other photons. So you can say, in other language, particles cannot leave each other forever. Maybe kind of love in the quantum physics. And even some physicists, just like Leo Susskind from Stanford, they believe that this is entanglement, which makes Einstein-Rosen bridge connecting two black holes. Anyway, but if you want to fully understand the quantum mechanically, the entanglement, we have to travel back in time to 1935. Schrödinger, he was the first person who used this word, and he introduced the concept of entanglement here in his seminal paper in 1935, and he counts 4 features for entanglement. First of all, they should have at least 2 degrees of freedom or 2 vector spaces, for example, polarization space and orbital angular momentum spaces. Physical properties should be characterized by joint function, which mathematically and physically we say is a tensor. Superposition of this joint function is important, just like this example. This is the wave function here, and you have f1 plus f2. And non-separability of this superposition is important. It means once you have entangled system, you cannot say this is the first photon, this is the second photon. No, this is entangled system. There is no way to express this entangled system as a product of individual subsystem. But this seems pure mathematics. So let's see how it works in experiments. Again, let's back to our EPR pair, Einstein-Podolsky-Rosen pair here. This is a state that we can describe this EPR pair. What is the meaning of this state? It means this state basically is a superposition of 2 possibilities. This is the first possibility, black one, and this is the second possibility, the green one. If you look at this photon here, it means in the first possibility, the photon 2 or the photon A in this picture can have the spin up or vertical polarization, while the photon 3 or the photon B can have horizontal polarization. And in the second possibility, it's just vice versa here. So now you want to share this entangled pairs between 2 parties. This is the first party and this is the second party. You send the photon 2 here and you send the photon 3 here, and you want to do the quantum measurement on photon 2. If after your measurements, and there's 50% chance because of this 1 over 2 here, if after measurement you find the polarization of photon 2 here and the vertical situation, immediately, right after that, without any performing measurement, and doesn't matter how far they are, you can say the photon 3 is going to accept this horizontal polarization. Or if you do the measurement and this system here, and the photon 2 here, and it accepts the horizontal polarization, immediately you can say the photon 3 is going to accept the vertical polarization. It doesn't matter how far they are. And this is exactly what Einstein didn't like, because it seems, at least, there is a kind of faster than light non-local correlation here between those photons. And that is the reason Einstein called it as a spooky action at the distance, because it was the time that he introduced the concept of relativity, special and general relativity. And basically, in this series, we can say there is a limitation in nature for communication. This is no one can go faster than light. Even information cannot go faster than light. That is the reason he and his postdoc, Nathan Rosen, and Podolsky in Princeton, they wrote this paper after Schrödinger, and they discuss in this paper that our observation cannot change the reality we measure. And later, he just showed his dissatisfaction with the quantum mechanics with the famous sentence that God doesn't play dice. And Niels Bohr, the famous Danish physicist who was a fan of quantum mechanics, he told Einstein, stop telling God what to do. In this paper, they introduced as entanglements Einstein, Podolsky, Rosen. Later, David Bohm, the American physicist, he assumed, okay, let's say Einstein is correct. So there should be a local hidden variable theory can justify this strange feature of entanglement. And we don't need the quantum mechanics, and quantum mechanics is complete. And John Bell, after David Bohm and Einstein, he accepted this fact, okay, let's say that this is the situation, and he derived some equations, and finally, it led to a Bell inequality. Collier and his colleagues, these guys, for the first time, they proposed experimental realization to test this Bell inequality to see if quantum mechanics is not correct and there is a kind of local hidden variable theory, just like David Bohm and Einstein opinion. And Alan Aspect, who got the Nobel Prize, he was the first person did the experiment, and he found that no local hidden variable theory can justify the entanglement, and all results confirming that local hidden variable theory either is not correct. Quantum mechanics might be correct, might be wrong. So far, so good. But if in the future, one of you guys just can find a powerful theory more than quantum mechanics justifying and probably can be unified with general relativity, for sure you're going to get the Nobel Prize. And maybe this is the reason that John Wheeler, one of the greatest physicists of all the time, he says that this is our observation that makes the reality. This is the act of measurement that makes the reality. It's not the common sense in our physical world, but in the quantum mechanical world, this is true. All having said, now this is the 29 March 1993. This is the day that Al Pacino, he got the Oscar award as the best actor for this movie, Scent of a Woman. If you have not watched this movie yet, I strongly recommend you to watch this. A very beautiful movie. But this is not all happened in that day. We do care about that. There's something more happened that day. This guy, Charles Bennett from IBM, and with some of his colleagues, they published one of the most groundbreaking paper of the physics, which can be considered as the first step for the second quantum revolution. They mathematically found the protocol that can be called teleportation today. It means an unknown quantum state can be disassembled into and later reconstructed by using two channels, the classical channel and the quantum channel. And we will see how it works. Years later after that, in a very fascinating experiment of history of science, in beautiful Innsbruck of Austria, Zellinger group, they did the first experimental realization of quantum teleportation. And it just started a new era in the quantum technology. And this is the paper we're talking about. It got published in 1997. And so far, you can say that it's received 6,837, maybe today even one more citation, who knows. And Anton Zellinger, he got the Nobel Prize later for 50 years contribution in the quantum entanglement and teleportation. After that, lots of progress happened. For example, some of the recent progress, which is very groundbreaking, Chinese scientists, they did a space-to-ground quantum communication network for more than 4,000 kilometers. Ground-to-satellite quantum teleportation for single photon also happened for more than 1,000 kilometers. Just very recently, they started realizing the quantum repeater-based quantum networks, which use the entanglement between two quantum memories, which is very important for future applications of quantum networks. And very recently, last year in Germany, they went for even larger distances, and the progress is huge. And every day we see something new in this aspect. But I guess the fair question to ask here at this point is why we need the quantum network and the quantum communication? Imagine years later from now, it's going to be the first commercial quantum computer. which is already IBM and Google. They have some very basic quantum computer. Of course, it's not the commercial one, but probably sooner or later it's going to be there. It's just a matter of time. Once you have the quantum computer, it means it gives you very surprising power, computational powers. For some of the problems that for fastest super classical supercomputer, maybe it takes thousands of years for them to solve those problems. You can solve using the quantum computer just using some hours, some days, or some weeks, the extreme case. Once you have this quantum computer, the classical communication cannot bring you security anymore because you would be able to break any kind of secret message here. And it poses a kind of security threat. So what you have to do is using the quantum communication because it brings you unconditional security. But how? As I described earlier, imagine this is the communication channel between Alice and Bob, and there's eavesdropper here. This eavesdropper wants to see the information and to see what's going on in this communication channel. But your information basically in the quantum communication scheme is a kind of quantum system. This eavesdropper, in order to get information about your message, he or she has to do the measurement, right? But based on the principles of the quantum mechanics, if you do any kind of measurement, if you try to do any kind of measurement on this information, on this quantum state, you're going to change it. So there is no initial state anymore. And this is the protocol that we call quantum key distribution. Fair enough, I guess this is the time that now we can focus on the Innsbruck experiment to see how these guys exactly perform the first realization of the quantum teleportation. Let's see again, what is the scheme here? We have Alice and Bob here, and Alice initially has this photon. She wants to Bob have exact copy of this quantum state here. And this is the entangled pairs EPR or Einstein-Podolsky-Rosen pair that I already introduced. And they have to share this EPR pair at the first step. But the first question is how they generated the entangled pairs at the first place. It is the spontaneous parametric down conversion, maybe the most famous way to generate entangled pairs. And by using the nonlinear crystal here, through a kind of nonlinear optical events, you can produce the entangled pairs. And this is the simplest setup that we use in our laboratory here at the Stevens to produce entangled pairs. But today, mostly we need those entangled pairs at the communication band or original bands, 1500 and 1300 nanometers. So that's the reason. Mostly today, we use a second harmonic generation process here. And then we send the output of the second harmonic generation to SPDC. But as you see in its name, this is a spontaneous event. It means there is no way to say when your entangled pairs are generated. But the only thing that you can say is just there is this relation between the output of the SPDC and the input. The output, which are the entangled pairs, signal, and idler, some of their frequency should be equal to the input. But we cannot say what is the wavelength because you can have lots of entangled pairs at the output. And this is the way exactly Zellinger group in 1997, they generated the entangled pairs. This is a picture of the experimental setup. Okay, let's see what is the meaning of this picture and how it works. At the first place, this is the UV light here, and this is the nonlinear crystal here. So just like the way that we do in our laboratory here in the Stevens, they sent this light to the nonlinear crystal. Spontaneous parametric down conversion happens here, and you're going to have one entangled pair, which consists of photon 2 and photon 3. And this is the state of that photon. The photon 2 is sent to Alice here. The photon 3 is sent to Bob. So far, so good. They already share entangled pairs, which is the first step in the teleportation experiment. But also, we need Alice to have this initial state here, because this is the heart of experiment. She wants to teleport this state. That is the reason. Once you send this light here, we have to generate the second entangled pair. For this light, also, there is a situation that some of the photons, which is in the fundamental mode, they pass through this nonlinear crystal without generating the SPDC, and they hit this mirror here. On the way back, they are sent to nonlinear crystal again, and they produce the second entangled pair here, which consists of photon X and photon T. This photon X is sent to Alice's site here after passing through a polarizer, which makes this initial state. And this photon T, basically, this is just for triggering the existence of this photon X to make sure that Alice already has the photon X and we can start experiment. There's one point that I would like to mention here. Alice doesn't have any idea about this photon X. This is an unknown quantum state for her. She doesn't need to extract information about this. She doesn't need to do the measurement to see what's going on about this quantum state. We just know because we prepared this polarizer here, but Alice doesn't know. So she wants to teleport a photon that she doesn't know. What is the state of that photon? That is the reason we say unknown quantum states. The second step is a real challenge, and it was a real challenge for Zellinger group at the time because generating entangled pairs is not a big deal. Today, we can do in all laboratories across the world. Of course, in 1997, the first time, it was really hard for them, but not that much a big deal. The real challenge comes at this step. You want to make the photon X entangled with photon 2, which is basically photon 2 is also entangled with photon 3. You want to make entangled of these 3 photons. It means you have to force these particles, especially photon X, to forget its past. They already exist, right? And once they become entangled, it means they have to lose their identity. There is no photon X, photon 2, photon 3 anymore. This is just entangled system. So the question is how they achieve this. So let's see what is the plan here. This is the photon X at this Alice site. Already Alice received this photon X, and already Alice received one of the entangled pairs, one of the EPR pair, which is the photon 2, but basically the photon 2 is itself entangled with photon 3. Alice has to superpose photon X and 2. It means she should have this state here. Maybe it seems a little bit tough, this equation, but if you look at this equation, it can be very simple. Basically, just don't care about this coefficient here because this is just probability coefficient. It's a superposition of 4 possible situations. This is the first one. This is the second one. This is the third one. And this is the last one. It means if you do the measurement on this joint state here, after measurement, you're going to find the system, the whole system in one of these possible 4 situations. So this is our state. And because the Alice has photon 1 and photon X or photon 1 and photon 2, so basically we can write the photon 1 and 2 in all 4 possible situations as one of the Bell states, which are the famous 4 entangled states in the quantum mechanics. And this is the state that Alice should have before doing any measurements. But how experimentally they achieve this state here? Okay, let's see. In this picture, you see a beam splitter, which is a semi-reflecting mirror. And the Zellinger group, they use this beam splitter here. If a photon, a single photon hits this beam splitter, there is 50% chance for reflection, this pass. There's 50% chance for transmission. Classically, you can say just it's going to be reflected or transmitted, but quantum mechanically, it's different. It's a quantum superposition, which is different with the classical superposition. It means this photon is in a superposition of being reflected or being transmitted. You cannot say which one happens. You can say just 50%, this one happens, 50%, the other one happens. Now, let's back to Alice setup here. If you look at this Alice setup here, this Alice has this one, right? This is exactly this picture here. We know that she already has the photon X and photon 2. And this is a semi-reflecting beam mirror here, or beam splitter here. The photon X coming from this side and the photon 2 coming from this side. Alice has to do the superposition of these photons, but now experimentally. These 2 photons, as you see, strike the mirror from opposite sides, right? And they pass a line so that the reflected path of one of the photons lies along the transmitted path of the other one. Classically, in the classical physics, it makes very sense that you can say there are four possible situations, consider reflection and transmission. I mean here, where these photons are ending up after being reflected or being transmitted. Here. You have four possible situations classically, right? But quantum mechanics is different. If you make sure that the photons are indistinguishable and the concept of time doesn't mean for them anything else, I mean, the arrival time doesn't matter for them, you can make sure that the quantum interference happens at this point. Once quantum interference happens, it means there's just 25% of the chance for these photons that they end up in separate locations here. While in the classical physics, it's 50% of chance ending up in separate locations here. Alice, this way, by superposing these two photons, she created this state here. But what is the next step? She has to do the measurement, Bell state measurement. So what she's doing at this step is she put two detectors here to do the Bell state measurement. What happens then? Once she's doing the measurement here, the whole wave function that I already talked about that, it's going to collapse to one of these four possible situations. And these four possible situations is just about the location that they end up. To make it simpler, I'm going to call these four possible situations as four probability, P1, P2, P3, and P4. Once a collapse of wave function happens, Alice already one of these possible situations. But Alice at this step need to tell Bob which of these probability is the result of her measurement. Because Bob wants to reconstruct the initial state, the initial photon, right? So she has to use a classical communication channel to tell the Bob the result of her measurement. In this measurement, there's 25% chance that P1 is the result of her measurements. What is the P1? P1 is the chance that you detect both photons at the separate detectors. And for the 75% of the time, you're going to have those photons at the same detector, right? Not the separate detectors. Imagine P1 is the result of the measurement. This is what happens after that collapsing of a function, or after that Alice performing the Bell-State measurement. This is the wave function of the system after that. It means Alice is going to have the entangled state of the photon 1 and 2, and this is what Bob's gets on his side. This is exactly the initial photon we wanted to teleport, plus one minus, the minus sign here, which doesn't matter in the quantum mechanics, it's just a phase factor here. How about the rest of the situation, 75% of the time? For that 75% of the time, Bob must perform a unitary transformation to get the initial state. Unitary transformation in the experimental quantum information, it just means a suitable combination of the half-wave plate and quarter-wave plate. So as you see here, teleportation works and mission accomplished. But I would like to mention a point here, which is very important, and this is the heart of the experiment. As I mentioned previously, you have to make sure that the quantum interference happens at this point, because quantum interference is different from the classical one. And if you don't have the quantum interference, you cannot have the teleportation works. You have to make this condition, photons are indistinguishable and arrive at the mirror at the same instant. But how practically, experimentally, they achieve that? Zellinger group, they use a smart way proposed by Zukowski from Gdańsk University in Poland. He proposed to use the Heisenberg uncertainty relation to make sure that the quantum interference happens. But how? And first, let's see what is the Heisenberg uncertainty relation. This is a strange feature of quantum mechanics. It says for non-commuting observables, just like position and momentum of a photon, or time and energy of the photon, which basically means the wavelengths and the time of the photon. there is no way to have simultaneous eigenfunctions for these operators. But what is the meaning of that? It means you want to measure the wavelengths of the photon. The more precise you want to measure the wavelengths, you're going to lose the precision about its time. And this is true also about the time. The more precise you want to measure the time of photon, the arrival time of your photon, you're going to lose its wavelengths. And this is the fact that Einstein didn't like. Observation affects reality. In their experiments, they sent the photon, based on his proposal, they sent the photons through a very narrow bandwidth wavelength filters. So what happened is, once it goes through that filter, the photons, they're going to have a very sharp wavelengths. You can say, for example, this one is 650, the other one is 850. But because of the uncertainty principle, they're going to lose their concept of time. So there is no arrival time anymore. You cannot say this photon is the first one, that photon is the second one. That is the situation you can meet the requirement for making quantum interference happens. And as a conclusion for teleportation experiments, we can say no physical principles has been violated. Quantum state of the initial photon, which is Alice wanted to teleport, has been teleported to Bob's photon. Now Bob's have the photon, but at the same time, Alice doesn't have the initial state anymore because now she has entangled pairs of the photon X and photon 1. That is the reason we say that no cloning theorem has been not violated. There is no photon X anymore on the Alice side. Just Bob has this photon X. So as you see, this is the beauty behind this teleportation experiment. Without physically transferring this physical photon, or even you can do the teleportation for electron or molecules here, big molecules here, without physically transferring that photon, you can have exactly the same photon at different places. And it doesn't matter how far they are. Maybe you want to do the teleportation from here to another galaxy. It works as long as you solve the problem about decoherence. Thank you for listening to my presentation. I would be very welcome to answer any questions you might have.
Thank you very much, Misach, for your very nice information. It was very nice to hear the progress that you made in your institute, and also generally the general information that we got from the concept of teleportation. So if you have any questions, please just unmute yourself and you can ask it directly, or you can put it in the chat box and I can ask myself.
Hi, thank you very much for the nice presentation. I had a few questions actually, but I'm going to keep it to one. You mentioned about the photon X, if I'm not wrong here. In order for Alice and Bob to have the same perception of what is the system, should they share any information? As if I remember, we called it the quantum key when dissolving the state. Should they exactly know what is the state of at least? Should they have the same information about A and B or the status of the X photon in order for this to work? Or there's no preliminary requirements for them to share a quantum key, basically?
Thank you so much for a good question. This is a very good question. In order to answer this question, I have to make a distinction between two quantum mechanical protocols. Here, we are talking about the quantum teleportation. For quantum teleportation, Alice doesn't need to share any information about the photons with the Bob. Actually, this is unknown quantum states here. But the second protocol is the quantum key distribution. Quantum key distribution is about sharing a secret key between these two parties, Alice and Bob. And they have to know about this one, because here you want to decrease the threat of the existence of the eavesdropper on the way, right? So you want to know exactly what was the initial state sent to the second party, and if there was eavesdropper here doing a measurement and changing the quantum state, so the receiver should know that. This is just different protocols. And in the second one, I would like to say yes to your question, yes, they have to share some information. But in teleportation, no.
Thank you, Yusuf. Any other questions? Okay, I have one. Regarding the speed of transmission of information between, for example, two persons here, Bob and Alice. So based on physics principles, there is no possibility of going faster than light. But in teleportation concept, we are talking about transmitting data in no matter of time. So I don't see, I got a bit lost in this sense that we cannot go faster than light, but on the other hand, we can transmit our data, we can transmit our signal in no matter of time.
It's a nice question, and thank you for question. First, I have to tell you something. As Richard Feynman says, in the quantum mechanics world, if you say why it happens, you're gonna trap your mind somewhere that you cannot run away from that. Because some of those quantum mechanical events, we don't have any logical justification for them so far. Exactly like about this faster than light correlation. The first person who complained about this, it was Einstein, because apparently it violates the special relativity. After Einstein, it's been, I guess, 80 years, and so far, there is a controversial debate between physicists, and there are two kinds of physicists at this point. The first kinds of physicists, they discuss that there is no a non-local correlation here, and they're just trying to find different ways to justify this non-local correlation at this point. And they say, because you cannot use this non-local correlation for communication faster than light, so basically it doesn't violate the relativity. But the second group of the physicists, they say, we don't know what's happening here. Maybe there might be a kind of non-local faster than light correlation between them, but we don't know why we have this one. Because at the first place, the nature of entanglement is not clear to us, why we have this entanglement here. But there is one thing that we can say for sure. Even if there is a non-local correlation here, faster than light non-local correlation, you cannot use it for making faster than light communication. Because Alice, as part of the experiment, Alice has to communicate with Bob through a classical communication channel. For example, writing a letter or sending email or making a phone call or something to tell the Bob about the result of her measurement. And this makes sense because if we had the faster than light communication here, and we could use that one, it's going to be violating the causality in the quantum mechanics, which is not good. So the real, and I would say the extraordinary, beautiful aspect of the teleportation is about you can make a copy of your physical object at different places without physically sending that or transferring that. But about this faster than light non-local correlation, honestly, nobody knows exactly what's going on.
Okay, interesting. And one more quick question about the interpretation of quantum physics. Based on my knowledge, at least I know that there are two different interpretations. One is many words, and the other is Copenhagen. So among these two, which one do you think is more accurate based on the recent results that you just mentioned from other groups?
Basically, so far there has been lots of interpretation for quantum mechanics. For example, agnosticism, Copenhagen, and local hidden variables theory by Einstein and David Bohm, and even many volts interpretation. What we can say is just, for example, the agnosticism, they say, okay, what's the point in asking question about something that we cannot get information? They mean, as long as you don't perform the measurement to get information about the physical systems, you don't have to know what's going on. This is the agnosticism. So they say just we don't know. Copenhagen interpretation, which Niels Bohr, he was in favor of that interpretation. He says, basically, there is no reality before our measurement, before performing the measurement. Once you do the measurement, you make the reality. This is our observation. The way we observe changes the reality. It might seem non-logical with our everyday experience, but so far we can say that experimental proof is in support of the Copenhagen interpretation, but there is nothing definite at this point. I mean, maybe one day in the future, one guy is gonna just bring a quantum gravity theory, can make a unification between quantum mechanics and general relativity, and then we have new answers, new interpretation for all these things happening.
Okay, thank you. Yeah, Tatef. Well,
I thank you very much for a talk, because this is one of the most talked topics, I assume, and especially after last year. I have a question, like regarding your point of view about the technological limits of teleportation and the limits of the pair source that actually let's say limit and define what can we do next.
That's a good question. Let me just get back to these slides here. This is one of the recent progress that happened in this field. They want to make entanglement sharing between different nodes at different places, right? Once you do this, it means it's a quantum network. And once you have the quantum network, you can perform the quantum communication between them. Quantum communication would be able to perform the quantum protocols like quantum teleportation or quantum key distribution as our first question, right? So, okay, having all this said, what's the point? What's the next step? The next step is going to be making a network of different quantum systems on different places on the Earth and performing the quantum communication between them. This is the holy grail of the quantum communication field, which leads to quantum internet. And this is what we want to get. And different places, and I know that lots of amazing group in the Europe, they have been doing lots of interesting research about the quantum communication, just like the University of Vienna. And they performed lots of beautiful experiments. And in China, they could be able to make quantum networks between satellites and some ground station. So yeah, I would say the quantum internet is the holy grail in this field.
I see. Oh, but do you think like the pair sources, basically the initial moment, the starting point, like the lasers, the I don't know, chips, the architecture of the photon production, basically correlated photon pair production, how limited it is?
I think
or we don't have any limits for that part.
I think the biggest limit in this way is loss. This is the biggest limit that we have, because you're talking for now about the 33 kilometers, for example, in this very recent paper, right? It's just about making quantum network over 33 kilometers. So the question is, if you want to have the quantum internet happening here, you have to increase the distance for more than 6,000, 7,000, 10,000 kilometers. So what would happen next? It's going to be a huge loss. Once you have the loss in your photons, it means you're going to lose information. So the loss is the biggest issue. So how they want to solve this loss? This is exactly this scheme you see here. It's a proposal by some physicists. They can use quantum repeater-based network. What is the meaning of that? It means you generate entangled pairs here, you do the frequency conversion on one of the entangled pairs to send it through the communication channel. But because this photon is entangled with the other one, so the other one already has all information, and the other one can be stored in the kind of ion trap or any kinds of quantum memory platform. It means even if the loss happens, you already have this information, and through performing the protocol like the quantum teleportation, entanglement swapping, or quantum key distribution, you can transfer this information to the destination. So now this is the milestone. They want to increase and increase the efficiency of the quantum repeater-based networks.
I see. Thank you. Thank you very much. Yeah,
worries.
hopefully it will happen. Huh?
Yeah, hopefully. There has been huge progress so far, and I think next 10 years or 20 years probably is going to be amazing.
Mhm.
Perfect. Thank you. Thank you, Tata, for your question. And thank you, Misa, for your answer. Well, is there any other questions?
I just had a very couple short,
Sure.
if you happen to know, kind of questions. I know it's not really related to the concept of teleportation, but more about entanglement. I remember in Armenia, it was 5 years ago, 6 years ago sometime, there was a scientist who was given a talk about entanglement of larger physical bodies rather than photons. Speaking of Stanger, like in electrons, and then moving forward to, he was saying that our goal is to have a couple molecules entangled in their vibrational states, and then move forward to even have viruses entangled and then different physical bodies. You talked about photons traveling for kilometers away. Do you think the physical reality would kind of sort of limit us to use only photons as the material for quantum communication rather than any other physical particles?
Photons have first I have to tell photons have lots of good points that you can use for quantum communication. One of the most important reasons they don't interact with each other. In the quantum optics, this is very important because lots of problems happens once you pose your quantum system against in front of the environment. It's going to be the open quantum system, very complicated mechanism, right? But the photons, they don't interact with each other, which makes a very good platform for the quantum communication. And about the first part of the question, you mentioned a very interesting point. Yes, making entanglement between big molecules. There's some groups I know that, for example, Walter group in the Vienna, or Dirk Bomister, who was the first author in the teleportation paper, now in Leiden, or in Netherlands, also in the Santa Barbara. They want to make big superpositions for molecules, for microscopic objects. So, but the question is why they want to do that? Because one of the problems that we cannot unify the quantum mechanics and general relativity is quantum mechanics happens in very small scales. General relativity happens in larger scales. So the question is, if you have big molecules entangled together, it means you can investigate the effect of gravity on the entanglement. Gravity is coming from general relativity. Entanglement is coming from the quantum mechanics. And I know that lots of groups are doing interesting research in this topic.
Thank you very much. That's good to know. And if there is time, I just had just another short question.
Sure.
I saw a lot of fibers in the setups, proposed setups. I happen to, like probably all of us here, work with fibers. They are absolutely nightmare in terms of stability, loss, and every other thing. As a matter of fact, something as trivial as Raman spectroscopy, we lose a lot of our precious Raman photons using a fiber. Given that loss is quite rightfully, as you said, the biggest challenge, why not doing all this in the vacuum of space so we can go very long distances? And with that in mind, is there any example of entangled particles discovered from space, basically generated naturally, not rather than in the lab?
I think also at the same time, there are lots of research about this part, because even those people supporting the idea of quantum repeater base, because for quantum repeater base, still they have to use the fiber, right? Some of those people, they just propose, instead of quantum repeater base, we can use the satellites on the orbit to make the quantum communication channel here. But also that has lots of challenges here, because in making connection with the satellites for now, it just happens in the limited case. At the part of my presentation, I told you about that Chinese scientist achievement for 4,000 kilometers. But if you start reading that paper, you see there is a weakness at this point. In each station, because they consider lots of stations on the Earth, and finally they connected all these stations on the middle station and the satellite. But in each station or each node, they converted the quantum information again to the classical information. It brings the security problem, because all you're talking about the quantum communication, it brings you unconditional security because it's quantum, right? So it's still, I know there are lots of interesting research going on about this part, but there are lots of challenges here. And maybe this is something funny, but once you're talking about the quantum mechanics, even you do one experiment now, half an hour from now, you're going to have different results. So that makes everything much harder.
If I may comment here, like, yeah, I totally agree, and I just know that an experiment has been that the guys tried to do experiment in the U.S., like sending photons in 20 kilometers, and it was a windy weather. So basically, there were so many noise and scatterings, and everything was so messed up. Experiment didn't work. So even the wind in like it was in one of the national parks in California. So it was like literally empty from humanity, empty from air pollution, but wind already didn't allow the experiment work. So, and vacuum in, if you don't speak about space, if you try to do it at least in the Earth atmosphere, there is no vacuum, and indeed already there we have some issues, right?
Yeah,
So
that is
like
true.
anything which is creating scatterings and losses, they affect the measurement result.
Yeah, that is true. I guess Paul Coit is one of the most famous physicists in the US. He's in Urbana-Champaign, and Daniel Gautier from Ohio State University. They're working on this topic, performing the quantum key distribution once you have the environmental noise. And at the same time, they're working on some proposals about the space communication, quantum communication in space. Yeah, we have to say which one works better, but I guess the power of quantum mechanics is extraordinarily interesting. And I'm sure it's going to be huge progress. It's just a matter of time, sooner or later, but it's going to be there.
Mm.
That's true. Okay, we are almost running out of time. So let's first take a group picture. So yeah, if you can just share your videos, guys, I would appreciate it.
Count before you take the screenshot.